So feel free to type in questions that you have, and we'll go over them. So type away, type, type, type. Can you guys hear me? This is more important than the Bachelor season finale. More important than your water polo scrimmage that you aren't allowed to play or something because you transferred. I'm watching this from the pool. Are we winning the scrimmage? No questions? All right, fastest GVL ever. Or we're done. Concepts. No other questions? Perfect. All right. Great GVL, guys. What? Stuff with equations, concepts. Yeah, that. Net ionic equations? You have to be more specific than just stuff. So net ionic, net ionic. Titrations. Okay, molarity or titrations or dilutions, something like that. What? Neutralization reactions. All right, I guess we could start with this, and then as more come, you could ask. Two of them. Yeah, that's a neutralization reaction when there's acid and a base. All right, we'll get started, and the more questions you have, just type them in. Everything. Be more specific than that, Bo. Shortcuts for the net equations? Perfect. We'll go over that for the net ionic. Wait, I guess net ionic and neutralization reactions are the same. So we'll go over it. For net ionic and neutralization, we are talking about when we're mixing an acid and a base together. So essentially what's happening during a titration. And there's really only three combinations that we will give you. We'll give you a strong acid, strong base. So that's one combination we'll give you. Another one would be strong acid and a weak base, and then weak acid and strong base. For the people here, do you guys want to know the full way or just the shortcut way of this? Full. All right. For strong acids, so we do an example of like HCl and NaOH. The long way would be, hey, you have to essentially mix them. HCl. I'm not going to bother putting aqueous. It's just going to take up too much room, but remember to always include states of matter. So I'll just put it. All right. And then at this point, remember, you have to double displace, meaning the positive is going to switch places. So we do arrow. I just don't have room, so I'm going to write it underneath. We're going to have HOH liquid plus NaCl. So that's step one, remember. Step one is to double displace when you can. So I'll write the rules like right here, I guess. Double displace. 2 is break up strong and ionic things. So next step would be HCl is a strong acid, so it would be H plus aqueous plus Cl minus aqueous. Sodium hydroxide is also strong, so Na plus aqueous plus OH minus aqueous. Water is a liquid, so we don't break that up. And sodium chloride is ionic. So now step 3 would be to cancel things out. We have an H plus, but no H plus on the product side. We have a Cl minus, and we have a Cl minus here. We have an Na plus, and we have an Na plus here, and that's it. So my overall answer would be H plus aqueous plus OH minus aqueous forms water. That's the long way. The shortcut way is understanding that if it's a strong acid or strong base, you'll always get certain ions. So since this is a strong acid, all strong acids can be written as H plus. All strong bases can be written as OH minus. Then all you have to do is either synthesize or single replacement. So then if we showed work, it'd be H plus aqueous plus OH minus aqueous. That's going to form water. So same exact thing as the long way, but now all you have to show me is that you know HCl is a strong acid, so it's going to turn into H plus. Strong base will turn into OH minus. Or the long way is just to double displace, then break up strong stuff and ionic things, then cancel out whatever's on either side. That's the general rule. That's about it. So let's give you some examples. So try these ones. Single arrow is fine for this stuff. Only time you really have to worry about single or double is when you do dissociation equations. right, let's go over some of this. All right, HF. If we do it the long way, we will see. We just do, well, we could just write aqueous, aqueous, and then we just double displace. So H is going to replace the Li. So we're going to get HOH in liquid. And then what's going to be left over is LiF. HF is a weak acid, so we're not going to break it apart. So HF stays together. LiOH is a strong base, so we're going to break it apart. Water is a liquid, so we're going to keep it together. And then LiF is ionic, so we're going to break it apart. Then the last step is to just cancel things out. HF is only on this side, so we have to rewrite HF. Li is on this side, Li is on this side, and nothing else. So OH minus, HOH, plus F minus. Simple. So like for the next one, yeah, for the shortcut, you just have to show me that you know what those things are, like strong acid, weak acid, strong base, or weak base, and show me what they would turn into. So really, the shortcut would go from you writing this weak acid, strong base, then somewhere showing me you know what they turn into, like HF, and then OH minus, then just ending up with the answer. So next one, HI, we know is a strong acid. And we know magnesium hydroxide is a weak base. But if we do it the long way, you double displace. So that it's going to be HOH liquid plus MgI2. Then we have to balance. We need 2 of these. That's 4 and 2. So we need 2 of these. Then strong acid, we break it apart. So the H plus weak base, we keep it together. Aqueous. Keep the water together. Yeah, this part right here. And then magnesium is ionic. Yeah. So then the final answer would be, cancel stuff out. We have, oh, that should be 2's here. 2 iodides, and nothing else. So it'll be 2H plus MgOH2 aqueous makes 2 waters. Liquid and Mg2 plus aqueous. Ah, not bad. And then the last one, if we do the shortcut, you would say, hey, this is the weak acid. This is a strong base. So I know the weak acid stays together. So I'm just going to write this. And I know calcium hydroxide could be broke, leave it at this. So then when I go about doing this, you just write, the answer would be CH3COOH aqueous plus OH minus aqueous arrow, just because I don't have room. CH3COO minus. Remember, we take off the H from the COOH part, plus HOH. The answer for the second problem is in blue right here. It is 2H plus aqueous plus MgOH2. The boxing helps. All right. That's the answer for one, not that one. Then this one, I just didn't have room to do it straight across. You did shortcut way. Do you know when to balance? How'd you balance here? CA, that'll be CA, 3, 2. Yeah, if you did shortcut way, as long as you showed your work, I wouldn't mind if you didn't balance. It's fine. Nice. Did you add water to your soap too at home? And Kaylin, were you able to read the answer a little bit better for the second one after I boxed it? Or do you still need me to read it? Yeah, perfect. All right, this is what we'll do. More practice or move on. If you guys are new to this, I use the do you want more time little poll. Um, so then you just click yes or no. Do you want more time? Yes means you want more time. No means we can move on. I always give you like 10-ish seconds. Guess we gotta get cracking. All right, so it looks like show the pool or the poll. It's a 60-40 split, so we're gonna stay. Wrong poll. POLL. Yeah. Bunch of different polls. So it looks like you guys want to stay. So let's do a little bit more practice. This one won't be that, or I can't make this go indefinitely. So we'll do some practice problem. Oh, practice, practice. Yeah, I'll list the acids, even though it's in our notes, Izzy. Yeah, this time I'll do one long way and then rest of the shortcut way. Yeah, the first one is sulfuric acid, H2SO4. Shall we go over? We shall. All right, H2SO4. So then we go like this. This is the long way. We know acids, or in this case, donate H plus. So this one's a little tricky in that you have to know it donates it. So this becomes, this one is tricky. Let's do the shortcut way for this one. So what I would do, I would say I would label this strong acid, weak base. So strong acid, we could just rewrite it as H plus, weak base, we rewrite it NH3. Then my overall answer would just be H plus, aqueous plus NH3. Aqueous makes this, just goes there. There's nothing to kind of like switch. Aqueous. The next one, this is a weak acid, strong base. So for this one, weak acid is, we rewrite it, H3PO4, aqueous plus. Strong base, we could rewrite it as OH minus. And then acid will donate one hydrogen, so you get H2PO4 minus plus HOH liquid. Could you do the long way? Switch H, HOH, K3PO4, that'll break apart. That doesn't break apart. It would just end up being NH4 plus. Yeah, positive. I guess multiprotic acids are a little bit tougher. Maybe I won't put these on the test. Maybe I will. Nobody knows. Except we'll see. Then, whoops. Rewrite it. Yeah, you just rewrite it when it's weak. So strong acid, weak base. Strong acid can be shortcutted to this. Weak stuff, you rewrite the whole thing. And then acid will donate, and then they have to switch places. In this case, they have to switch places because there's something in the plus spot. So water takes over, and iron is left all by its lonesome. That's a weird 3 plus. Then that's 4 and 3. That doesn't really match up. Three. So let's try this as a 2, 2. 2, 4, 3. Oh, 3. I don't need this. I don't need this. So that's 6. I just need to put a 3 here. That's just me balancing. 3, 6, 6, 3, 3, 1, 1. Do we have to balance? Yeah, you always have to balance. I gave you weird examples. I should give you better examples, shouldn't I? Let's see if I can find better examples so I don't make it up on the spot. Blah, 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 blah. We'll try this one, and then we'll move on. Let's do bicarbonate and so write the net ionic or the neutralization reaction for bicarbonate and let's go with, then we'll do one more. We'll do HCO3 minus plus. Try this. Two different problems. HCO3 minus plus HCl. Nope, it's not. Yeah, NaOH. You guys want more time or should I go over this? Let's go over it. So in this case, you have to know that sodium hydroxide is a strong base. That automatically means that this one has to act as an acid, and since it's not any of our strong acids, it's going to be a weak acid. So if we did it the long way, weak acid, we would just rewrite it. I'll just start on the other side. We have to flip-flop. So the acid's going to give up the H plus, but there's already a positive part here, so we have to kick that off, and that's going to go here. So this is how you do that double displacement. So then we are going to get NaCO3 minus. I guess it could be 2 plus, but it doesn't really matter at this point because we're going to break it apart. Plus HOH liquid. Then when we break things apart, since this is weak, we keep it together, HCO3 minus. Plus, it's a strong base, we break it apart. This is ionic. HOH. Crossing is out. That crosses out. That crosses out, leaving us with HCO3 minus aqueous plus OH minus aqueous makes the carbonate ion and water. So if you wanted to do it the shortcut way, what you would have done is, hey, I know this is a weak acid, so I'm just going to rewrite it. I know this is a strong base, so I'm just going to write it as OH minus. And then you just have to remember what acids and bases do. Acids will donate an H plus, and bases will receive it. So the next one is, hey, we know HCl is a strong acid, and that's a weak base. So if we do the shortcut method here, we could just bring down the HCO3 minus. We know the strong acid will turn into H plus. And we know acids are the one that will donate here. And in this case, you can make carbonic acid. Here's the thing, if you then know what carbonic acid does, you know it'll dissociate, but as of now, this is fine. See, that's where things could go awry because in the first one, HCO3 minus acted as an acid. The second one, it acted as a base, meaning HCO3 minus is what? No. Amphoteric. It can act both as an acid and a base. Aiden, your answer is not wrong. You just went one step further, knowing that carbonic acid would break up into water and carbon dioxide. But most people don't know that. Yeah. All right. Let's move on. There could be an amphoteric one on the test, but if you're not sure what that substance is, the other one should definitely let you know if you should know if it's acid or base, then the other one has to be the flip of it. When do you know it's amphoteric? In this specific situation where I give you two equations And in this first one, it acted like an acid. And in the second one, it acted like a base. But it's the same substance, so that's how you know it's amphoteric. All right. We'll do the conjugate acid, conjugate base stuff. This one could go quickly. Oops. We spent 35 minutes on what did we just talk about? Oh, neutralization equations. Next, we will go conjugate acid, conjugate base. So that one's a good one. So HCO is yeah, we're also spending tomorrow working on the lab. Bad example. Let's just have a bunch of review stuff. Ammonium. Let's do that. Things that we don't really see. Question is to label the following as an acid-base conjugate. Acid conjugate base. And remember, to keep this simple, just have one side always be your conjugate acid, conjugate base side. So for me, I just always make my initial product side always going to be my conjugate something, conjugate something. Then to figure out what everything is, you have to remember two main things. What do acids do and what do bases do? Those are the two main important questions you need to know in order to solve these types of problems. Yeah, so acids will donate or give, and bases will take or accept. So let's look at this first example. We have HSO4 minus, and we look on the product side, it most likely became what other substance on the product side? Yeah, it most likely turned into the SO4 minus, so they're most similar to each other. So now, when you think about it, you have to think about, okay, in order for this to become this, what did it have to do? The HSO4 minus had to give up an H to become SO4 minus. That means HSO4 minus acted like an acid. It gave away an H plus. So this is my acid. So we go on the flip side. our F minus most likely became HF. In order for our F minus to become HF, it had to accept an H plus. That means this one acted like our base. So now this is where students find trouble, is when you have to go backwards. When you have to go backwards, you do the same exact thing, but now you're starting with your product. So now I'm starting with SO4 minus, and I eventually want to turn it into HSO4 minus. In order to go from SO4 minus to HSO4, so SO4 minus, to turn it into HSO4 minus, it had to take an H. So that means this acted like our conjugate base. And then the flip side, in order for HF to turn into F minus, it gave an H, making this our conjugate acid. So that's really it for these types of problems. It's just remembering, okay, what do bases do? What do acids do? Will there ever be two acids on the same side? Nope. So that's also another good thing, where each side will have one acid and one base, always, for the problems that we'll be giving you. Two minutes. So titration. So the lab that we just finished up today, the whole point of a titration is to get to the endpoint for us. Technically the equivalence point, but let's not worry about that. At the endpoint, that's when the color started to change. That's when moles of acid equals moles of base. To find the moles of acid and moles of base, we usually know the molarity of the acid and the volume of the acid, and then molarity of the base, volume of the base. We know that because, I guess I should have showed a little bit. Because we know the molarity is moles over volume, in this case liters. So if we want to go to the moles, we multiply both sides, so that moles equal molarity times liter. And liter is just a unit of volume. So MV equals MV. That's really it. So if you're given a problem where it says, I'll just make this into like a lab question. Start and let's see, you started at 0.0, let's make it a little bit, 0.2 milliliters, and you ended at 19.1 milliliters of questionable molarity base. We don't know. But you do know the hydrochloric acid is 0.977 HCl. And you use 10 milliliters of it. How do we find the molarity of this base? So the whole point of the titration, remember, was to get to the endpoint. At the endpoint, moles of acid equals moles of base. So that's why M times V equals M times V. We know the molarity of the acid, 0.977. We know the volume of the base that we pipetted, 10.0 milliliters. We don't know the molarity of the base, but we can find the volume of the base. So if I started my line at 0.2 and I ended at 19.1, how can I figure out how much base I used here? What math would I have to do? Yeah, you just have to subtract. So the amount of base I use would be the final minus the initial, which is just 18.9. This becomes 9.77. Divide both sides by 18.9. That means the molarity is 0.517 molar NaOH. So the main thing about titration is just remembering that the endpoint is where the moles of acid equals the moles of base. Yeah, you can just do it once. So now let's say you're given a problem where you now found the molarity of your base. We know it's 5.17 molar NaOH. But let's say you used 0.58 grams of a mysterious acid. And you titrate it, and your starting titration was like start and 0.2 to 31.6. So the thing here is we want to know the molar mass of our acid. And what are the units of molar mass? Yeah, grams per mole. What do I already know about my acid? Yeah, we know the mass of our acid. So we already know the grams. So all I have to figure out in order to find molar mass is what? Yeah, the mole. So we have to figure out the mole of acid. But literally the only thing you know is the mass of acid. You know nothing else. You're like, oh, great. Why did we titrate? And what's the main point of a titration? To get to where? The endpoint. And what's true at the endpoint? Meters equals meters? That's weird. Moles of acid equals molarity equals molarity? That's not true either. Moles of acid equals moles of base. So that means in order for us to find moles of acid, what actually do we have to find? In order for us to find the moles of acid, what do we have to find? We have to find moles of base. So in order to find moles of base, what do I know about my base? There's two things I know about my base. Yeah, we know the molarity of the base, and we could find the volume of the base that we used during our titration. How do I find moles? Yeah, remember, moles is molarity or moles over liters. So to find just moles, it'd be molarity times liters. Can you use milliliters here? No, so be careful. So 0.517 molar times, in this case, our liters, or actually our milliliters, would be 31.6 minus 0.2. This gets us to 31.4, but this is in milliliters, so all we have to do is change it to liters. Then if we do this, we get as our moles 0.01623 dot 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 moles. Then the very last step to find molar mass would be to do our 0.58 grams over 0.01623 dot 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 moles, which gets us what you guys get. 36 grams per mole. Any other questions? Lost? Nothing? Everyone's good? pH. That's another huge topic. 42 minutes to 53 minutes. Another one of these. You're in my class. We'll practice tomorrow. All right, another huge thing is pH. So you could be given two things to start off with. You could be given the molarity of an acid, or you could be given molarity of a base. So I already showed my kids this, so we'll do this part really quick. Molarity of the acid is going to be the molarity of H plus. Molarity of the base will be the molarity of the OH minus, but you have to multiply the number of OH minuses here. And the first things that you probably learned was the relationship between H plus and OH minus. Between here would be 1 times 10, let's add more stuff. This would be H plus times OH minus equals 1 times 10 to the negative 14. So that's how they're related to each other. Then if you know H plus, you can find pH. To do that, it's just a negative log of H plus. And if you're given pH, the anti-log is 10 to the negative pH. Ah. Similarly with OH, you can find POH. POH is the negative log of OH minus. And to go from POH to OH minus, it's 10 to the negative pOH. Then the easy relationship between pH and pOH is pH plus pOH equals 14. So this is a pretty handy little tool you could use when it comes to doing any pH problems. So I could start you off with a base, and then from that base you should be able to find pH, pOH, and H+, all of them. So let's practice. Let's see. Given 0.847 molar calcium hydroxide, find everything. Find pH, pOH, H plus concentration, and OH minus concentration. Ready, set, go. Correct. Calcium hydroxide, CaOH2 is a base. Oh, did I make the base too strong? Technically, yes. That means that this is a bad example, isn't it? This is what happens when I try to make problems like this. Here, this is what we'll do. Let's see. It's too small. Okay, I thought I did it wrong. How can I make this? Let's change it so that it's 3.47 or 0.347. Does that work better? 0.347. What is that? Unreal answers. Liar. That's. Ah. Mm, hopefully, I find better examples for you to test. Yeah, since you guys already started. We'll just stick with this. The POH is super small. Yeah. pH to H plus is pH is 10 to the negative pH. So we'll do this. So you have to know that we were given a base, and if it's a base, this gives us our hydroxide concentration, but we have to be wary of how many hydroxides there are. So in this case, there's 2, so we have to multiply by 2. So 0.347 times 2 would get us 0.694 molar with correct units. So now if you think about our pH box, now we have our bottom right corner, which is OH minus. Depending on which way you want to go, you have multiple different options, but seems like majority of you probably went the OH to the POH to pH to H plus route, so we'll do that route. To find POH, it's the negative log of OH minus, which we just found, so it's going to be negative log of 0.694, that's a 9. And that's going to give us probably the answers that you guys got, negative log of 0.694, a terribly small pH, or POH, 0.159. So that's our POH. Then we could go, so now we have our top right corner. Majority of you probably went to the next to the top left corner, where the relationship is, hey, I know that pH plus POH equals 14. So pH plus 0.158.6 equals 14. So pH would be 14 minus that, and you get 13.841. So that's my pH. So you only multiply the amount of OH minus from the beginning. So the only time you have to worry about multiplying the initial given concentration is for a base if there's more than one. So if you go back to our chart right here, this part right here is when you have to worry about how many hydroxides there are. Every other time you don't really have to worry about it. It's just this, you have to worry about it. So like for acids, like if you were given a concentration of acid of 0.100 HCl, you could just put that directly into the H plus, and that one would be 0.100 molar for H plus, like that. So the only time you have to worry about multiplying is for just bases. That's it. Then the last step is to find the H plus, and that's going to be 10 to the power of the negative pH. So then this would be 10 to the negative 13.8413 dot dot dot. And if we do that, we get 1.44. How many six figures? 1, 2, 3, 4, 5. 0, 9. That's a 4 times 10 to the negative 14th molar. H plus. All right. So 1, 2, 3, 4. 4 different answers from this one problem. I'll give you guys one more problem, and I actually have to go. So, uh, what can I do? Do you subtract 14 from POH? Yeah. So, this case, the relationship between pH and POH is if you add them, you get 14. So let's say you had like a pH of 8. That means you just really just plug it in where it's 8 plus POH equals 14. Subtract 8 from both sides. So the POH in this case would be 6. So this time we'll start off with an acid. So find the concentration. So find everything if you have a concentration of HCl to be 0.0123 molar. So find everything. pH, POH, H plus, and OH minus. So, since hydrochloric acid is an acid, the concentration of the acid will be the same as H plus. So you can just rewrite. So hey, H plus is 0.0123 molar. From there, we have two different options. In this case, I'll go all the opposite directions we went on the last problem, so you guys could see the different ways. So I know the relationship between H plus and OH minus is if I multiply them, it equals 1 times 10 to the negative 14. We know what H plus is. It's 0.0123. So I'm solving for OH minus. Divide both sides by 0.0123. And we get, if I show all my work, OH minus is 8.13 times 10 to the negative 13 molar. And we know that pH is the negative log of H plus. And that would be negative log of 0.0123. And that's based on all of your work. Sounds like negative log of 0.0123. 3 phase 1.91 pH. Then last thing for POH, I guess POH is negative log of OH minus. So it'd be negative log of 8.13 times 10 to the negative 13. That's not the exact answer. X to the 0.023, negative log of this. You get 12.1 as our POH. Yeah, and then depending which way you go, your sig figs can vary a little bit. But your answer should be relatively close to this, off by the last digit of the significant figure. And even it being a shorter GBL, we actually went through all of the major topics. But yeah, I have to go. But we need a code word. Oh yeah. Figure out a code word as I end the recording so that I could send out the reminder.